get familiar. So if you don't know by now, then you should probably get familiar.
Hello students, so welcome back to my video. I think this is the video number 6 for you. Okay, so let us consider the concept called time dilation in this part of the video. So now, to understand the concept of time dilation according to the theory of relativity, so as usual we have to consider two frames of reference, right? So one of the frame is considered as the frame S, okay, and that frame is assumed to be a stationary frame of reference. It is having the coordinates x, y, z, and the observer in the frame of reference S is considered as the observer O, correct? And then another frame of reference is S dash, and it is assumed to be moving with the velocity v bar. So along the x-axis the frame S dash is moving in one direction, it is moving. Okay, so in this regular consideration, so now we have to discuss how the time intervals are measured with respect to two frames of reference. One is fixed frame of reference, other one is moving frame of reference. Okay, so for that what I am considering here is an event. So let us consider an event occurs in the frame of reference S. So that means in the fixed frame of reference I am considering an event. So it may be, let us say, glowing of a bulb, or maybe a signal. Okay, so periodically it is happening, or a bell, okay, continuously it is ringing, whatever it is. So now let us consider such an event occurs twice. Okay, an event occurs twice in a stationary frame of reference in a particular place. Okay, so at the point, let's say the point P. So this position will not change with respect to frame of reference S, isn't it? So now at the particular point P, what are the time difference between the two events occurs at the point P now? So you know that the time can be measured as T1 and T2 between the two events with respect to frame of reference S. And similarly, the same two events are measured by an observer O dash, okay, who is moving with the frame of reference S dash. So what are the times are measured? T1 dash and T2 dash, okay. And if you know the time difference, okay, if you calculate the time difference between the two events, so with respect to frame of reference, it is equal to T2 minus T1, that is equal to T0, and you can take the T0 as the proper time, because the event is occurring in the frame of reference S, and hence we call it as proper time. The same time difference, okay, the same time gap or time interval you can say. So that is what we are measuring with respect to S dash is now given by T2 dash minus T1 dash, let it be capital T. Now the events are same and the time gap is also same, but measured by two observers here. So measured by the observer O and O dash. Now the question is whether these two time gaps, okay, measured by two frame of reference T and T0 are same or not. Okay, if they are same, if T is equal to T0, then what we can say, there is no difference in the time interval measured by a fixed frame of reference between the two events and the same time interval measured by the moving frame of reference. Okay, if there is a difference, then we can call it as there is a time dilation. Okay, so in the time dilation, so we are expecting that the moving frame of reference is measuring the longer time compared to the time difference measured by the fixed frame of reference. So okay, that is what you have to prove here now using the Lorentz transformations derived in the theory of relativity. Clear? Okay, now let us proceed. So with respect to this diagram, as I said already, so let us consider now if T1 and T2 are the two events occur at a point in the fixed frame S, okay, then the same two events measured by an observer in the moving frame of reference S dash will be T1 dash and T2 dash. Okay, please note down that T1, T2 are the times measured by the frame of reference S, T1 dash, T2 dash are the times of the same events measured by the observer in the moving frame of reference S dash. Okay, so with this consideration, now I will proceed to calculate the time interval. Here I will write the time interval between the two events with respect to S first. That will be equal to T0, T2 minus T1. As I told, it is a proper time, correct? It is a proper time. Now, what is the time interval measured by an observer in the frame of reference S dash, that is t is equal to t2 dash minus t1 dash. Okay, it is a measured time with respect to moving frame of reference. So in order to measure the times t1, t2, we have a clock here in the fixed frame of reference and the clock is fixed here. So to measure the same time intervals in the moving frame of reference, again there is a clock with the moving observer also. Okay, so this clock is measuring the same time intervals as t2 dash minus t1 dash. Let it be capital T. Now use the Lorentz transformation equations. What is that? So Lorentz transformation equations gives t1 dash is equal to, you know that, t1 minus vx1 by c2 c square divided by square root of 1 minus v square by c square is the equation. Because if it is t, then we will take the position x here. So now we are measuring the two events here. So with respect to the fixed frame of reference, moving frame of reference t1 dash, that is equal related to t1 as t1 minus vx1 by c square divided by square root of 1 minus v square by c square, where v is the velocity of the moving frame of reference and c is the velocity of light. Okay, similarly t2 dash is related to t2 minus vx2 by c square divided by square root of 1 minus v square by c square again. So denominator is same. Okay, now if I take the difference, because you have to get the time interval here. Okay, so just take the subtraction, subtracting the above equations, we get t is equal to, okay, directly we will get t, because t2 dash minus t1 dash is equal to what here? T. So therefore t is equal to t2 dash minus t1 dash. So in the above equation, the denominator LCM is equal to square root of 1 minus v square by c square. So it is a simple arrangement of the numerator equation, that is t2 minus t1, okay, and v by c square is common. So in that, if you take v by c square is common, left with only x2 minus x1 in the bracket. Correct? So note down the equations up to equation 3. Okay. Now look at here. The clock in the frame S remains fixed at a point. That means whatever the event occurring in the frame S, so we are fixed a clock here, and hence the position of the event will be same. So that you can say x1 is equal to x2. So if x1 is equal to x2, then in equation 3 we can cancel this x2 minus x1, correct? Because they are equal. So this term will go. So what is the remaining term? So we can write now t is equal to, so because t2 dash minus t1 dash is taken as already t, and this t2 minus t1 difference is taken as t0. Okay, so therefore left with t0 divided by square root of 1 minus v square by c square, right? So we can take this constant as gamma here. So gamma into t0, let it be equation 4, where gamma is equal to what? So we are taking 1 by square root of 1 minus v square by c square as some constant factor, that is gamma here. So that means the time measured by a moving observer between the two events is equal to gamma times of the proper time measured by the observer in the fixed frame of reference, that is t0. Okay, so now what is the conclusion here? So you can see that the denominator factor square root of 1 minus v square by c square is always a fraction, that means less than 1, right? So since square root of 1 minus v square by c square is always less than 1, so we can see that the relation t is equal to gamma into t0 indicates that t is always greater than t0, because the fractional value is multiplied to t0 here. So by cross multiplication you will get, so t will be greater than t0. Okay, so with this observation we can conclude that the time interval t measured by an observer in the moving frame is always longer. Okay, you should see that here, it is always longer. Okay, it is measuring the larger time. Okay, so longer than the time interval t0 measured by an observer at rest, okay, with respect to the clock, right? So this phenomena, that means the difference between the two time intervals measured by s and s dash is not equal here. So t is observed as greater than t0, so that phenomenon is called time dilation. So dilation in the sense it is making larger. Okay, so because time is measured longer with respect to moving frame of reference, that is why it is called time dilation. Clear? Okay, you should remember that a moving clock, you can understand that here, a moving clock always ticks more slowly because it is measuring longer time, so it ticks more slowly than a clock at rest. So that is the final conclusion in the concept called time dilation. Clear? So because it is very interesting to see theoretically, but what is the experimental evidence? So in the next video, let me explain one experimental evidence for this time dilation. Okay, then see you in the next video.